First thing we want to do is draw out the problem right here. So we have a uniform line of charge of a length L and a charge density of lambda. And we have a point P right here of interest, y above the very top of that line. So we're going to go ahead and just label this line as length L, lambda density, and P is y above the top of the line. And we're going to go ahead and use the variable r to indicate a distance from P to every point in this little line here. So the three variables that we do know that's given in the problem is the length of the line L, the distance P is from the top of the line, which is y, and the line charge density of lambda. And we need to find the voltage or the potential at point P because of that line. So the first thing to do is to write out the definition of voltage in terms of Q. And it's going to have to be in terms of an integral since we are looking at a distribution of charges. So this is the equation for the voltage in terms of charge dq and r. R being an arbitrary distance from P and dq being little infinitesimal charges within that line. First thing to look at is we want to get dq in terms of r so that we can actually do the integration. What we can notice here is that, and this is usually what you have to do anyway when you are looking at these types of integrals, is that you never really integrate with respect to dq. That rarely happens, if even. What you do is you get it in terms of lambda and some sort of spatial component, right? So as you might have recalled earlier, lambda is some sort of infinitesimal piece of charge over some infinitesimal space, which we will call dr. That is the infinitesimal space that we are indicating here. And we're going to go ahead and indicate that space from y to y plus L. So that just means that we are making this dr go all the way from a distance of y from P all the way to a distance of y plus L from P. Okay? So that means that if you were to go ahead and solve for dq, that would simply equal to lambda dr, where we can say r goes from y to y plus L. And that would, integrating this, would basically give you the entire charge of this line. Now we're going to go ahead and plug in dq into this integral, which is the voltage integral, from that same limitation. So now we have V, capital V, is 1 over 4 pi epsilon naught, integral of 1 over r times dq, which is just lambda dr. The integration, again, is going to be from here, which is y below P, to y plus L below P. So the distance of y to y plus L away from P is how we're going to integrate or do the limits of integration. Lambda is a constant, so we're going to pull that out, and we will have lambda over 4 pi epsilon naught integration from y to y plus L of 1 over r dr. This looks familiar. If you integrate 1 over r dr, it becomes a natural log. So V is now going to be lambda over 4 pi epsilon naught. Natural log absolute value of r from the limits of integration, y plus, or all the way to y plus L. Cool. Now let's go ahead and plug in these values for r. You're going to do this whole function here, where r is y plus L, minus this whole function here, where r is just y. And that's how you analyze the limits of integration. So this ends up being lambda over 4 pi epsilon naught, natural log of y plus L, minus natural log of y. The laws of natural log say that if you have a natural log with an argument minus another natural log with another argument, it's equal to a natural log of the first argument divided by the second argument. That's the law of natural logs. Let's go ahead and replace this with that, and we end up getting the final answer. Voltage is lambda over 4 pi epsilon naught, natural log, the absolute value of y plus L, divided by y. And I'm not going to simplify it anymore. I'm not going to say this is 1 plus L over y. I think this is good enough. So we got it we got the final answer, the voltage in terms of lambda, which is right up there, y, and L. And that's the voltage experienced at point P because of this distribution of charges.